So let's start with molecular orbital theory. So molecular orbital theory, as we have discussed before, is that we view the molecule having the same concept as atom having atomic orbital. So in short, that the total number of electrons in a molecule can be distributed, can be arranged according to the way that we arrange electron in atom. And we have discussed the three principles in chapter 1. So that is how you're going to use the same principle to arrange the number of electrons involved in the molecular orbital to be in that electrons involved the molecule to be arranged in the molecular orbital. So if you look at this, there are a few terms that you have to understand. One is bonding molecular orbitals. The other one is anti-bonding molecular orbitals. So keep in mind that you have two types of molecular orbitals, which is bonding and and another one is anti-bonding. So what is bonding molecular orbitals? Is the electron density builds, means that the highest electron density is there, whereas the anti-bonding is cancellation of electron wave. So this is where the electron density is very low. So if you look at in a form of diagrams, so anti-bonding is where destabilization occur. So you can see the area is less dense with electron, whereas the bonding is where the electron is concentrated. So this is more on theoretical of how molecular orbital theory view the concept of covalent bond. So this is due to construct, if you remember that electron is in a form of wave, can be in a form of wave as well as particle. So this is where the wave concept comes in. You have constructive wave where bonding is orbital occur, and destructive wave where the anti-bonding occur. So if you look at here, remember that I said electron in a molecular orbital can be arranged according to the same principle on how you arrange electron in atoms. So it's the same principle. One is electron fill the lowest energy orbital first, and maximum 2 electrons per orbital with spin paired, and electrons is spread out as much as possible with spin unpaired first if the energy of the orbital is the same. So if you look at this example, this is example of the name of the molecular orbital. You have sigma 1s and sigma star 1s. So sigma 1s represent the bonding orbital, and sigma star 1s represent the anti-bonding orbital. So the anti-bonding orbital has higher energy, if you remember this one, okay? The energy is higher, okay? And let's say if we have hydrogen, okay, we have hydrogen. So this hydrogen contribute 1 electron and this hydrogen contribute 1 electron. And according to this series of molecular orbital, you have sigma 1s, sigma star 1s, and so on. But since we only have 2 electron, 2 total of electron, so you fill up this one first, sigma 1s, and then you pair it, so now it is already full, okay? So there is no more electron to be put inside the second orbital, which is higher energy than sigma 1s. Let's say if we have another compound or molecule, helium-2. Okay, now helium contribute 2 electrons and another helium contribute 2 electrons. So there are 4 electrons now. So if we arrange the electrons, we arrange first 2 here, 1, and then pad another 1. So we have another 2 electron. So we're going to arrange another 2 electron in the higher energy level molecular orbital. So now, since we have only 4, so this is a complete version of the molecular orbital energy level diagram. Okay, before we proceed, let us look at this video showing that the diagrams on how molecular orbital theory related to the diagrams. So let us look at
bonding orbitals, or sigma star and pi star anti-bonding orbitals. This theory ends up being better equipped to predict the arrangement of electrons in a molecule in certain situations. This is due to a process called the linear combination of atomic orbital. In the modern physics course, we talked a little bit about the wave function, and molecular orbitals are combinations of atomic orbital wave functions. Just the way the wave function describes the behavior.
Remember the word wave function. So it's a combination of atomic orbitals wave function.
Of an electron within an atom, molecular orbitals describe the behavior of an electron within a molecule. And just like atomic orbitals, they are filled when they contain 2 electrons of opposite spin. This theory requires that we strongly consider the wave nature of the electron. In the classical physics series, we talked a lot about waves and interference patterns. So to get the full picture of wave behavior, in order to better understand molecular orbitals, check out this tutorial now. Otherwise, we simply need to understand that when 2 atomic orbital wave functions are combined, like these 2 s orbitals, there can be constructive interference, where the peaks line up with the other peaks. This causes the amplitude to increase, which results in a bonding molecular orbital, like the sigma s orbital. Most of the electron density is between the nuclei, which strengthens the bond. There can also be destructive interference, where the peaks line up with troughs. This causes the amplitude to drop to 0, resulting in an anti-bonding orbital, like this sigma s star orbital. Here, there is a node between the nuclei, which weakens the bond. The bonding orbital is of lower energy and will thus be filled before the anti-bonding orbital. For this to make more sense, we simply need to understand that these images of waves are just 2-dimensional analogies to help us visualize the type of overlap.
Right.
Electrons are 3-dimensional objects, so the waves are in 3 dimensions, and constructive interference thus results in regions of greater electron density, while destructive interference results in regions of no electron density, which are depicted by these bonding and anti-bonding orbitals. We can do the same thing with p orbitals, utilizing direct overlap, which will yield sigma px and sigma px star molecular orbitals, or lateral overlap, yielding pi and pi star molecular orbitals from the overlap of py and pz atomic orbitals. Orbital number is always conserved, which is why the linear combination of 2 atomic orbitals will always result in 2 molecular orbitals, one bonding and the other anti-bonding. We can depict these linear combinations with molecular orbit.
Okay, so this is called molecular orbital diagram, the one that I've shown you in the slide. Okay.
Diagrams, as we have seen. The dashed lines show how the atomic orbitals on the sides combine to form the molecular orbitals in the middle, such as we see here for hydrogen, with 2 1s orbitals combining to form 1 sigma s orbital.
Okay. So you can see this electron from 1s from this hydrogen, and this electron 1s from this hydrogen. We have 2, and now how do we arrange? We arrange according to the lowest energy first, which is sigma s, and the second principle requires us to fill up a maximum of 2 electrons per orbital. So we fill up 2 electrons per orbital with spins paired. So you can see now the spins are paired. Okay, so this is the bonding orbital, and we have no more electron to fill up here.
Orbital and one sigma s star orbital. If we go up to the electrons in the n equals 2 shell, we can see the 2s orbitals combining in precisely the same way, and then the 2p orbitals combining as follows, with the sigma bonding orbital and then pi bonding orbitals, followed by the corresponding anti-bonding orbitals. The good news is that these orbitals are still filled according to the Aufbau principle and Hund's rule, like we already know. This means that we fill them from lower energy to higher, according to Aufbau, and we will put one electron in each orbital for a set of degenerate orbitals before doubling them up, according to Hund.
Okay, degenerate orbital means that the orbital is the same energy. For example, if we have this pi molecular orbital, we have to fill it one first, and then another one here before we pair the orbitals, pair the electron with another electrons, okay?
We've already learned in a previous tutorial how to fill in these MO diagrams for certain diatomic molecules, like O2, and how to use them to calculate bond order. Here's that diagram one more time, along with the calculation for bond order, with 10 bonding electrons, including the sigma 1s bonding electrons, and 6 anti-bonding electrons, including the sigma 1s star anti-bonding electrons. 10 minus 6 is 4, and 4 over 2 is 2. This explains the double bond in diatomic oxygen.
Okay.
But we also get an explanation for the parametric.
Right. Okay, I would like to share the concept of bond order. So it's a very important principle in molecular orbital theory, is how to calculate bond order. So bond order is used to identify whether the compound or the molecule actually exists, can exist according to the actual condition. So let's look at how we calculate bond order. So this is a formula. So bond order is the total number of electron in bonding domain. So you just calculate all electron that is in the bonding domain. For example, here is 2, okay? Minus the anti-bonding electron, all electron in the anti-bonding. So here is 0, so minus, and divide by 2. So now the
electrons in anti-bonding orbitals divided by 2. Here, that gives us a bond order of 1.
So now we have a bond order of 1.
Which is why H2 has a single covalent bond. Now look at O2. Each atom displays its electron configuration, and every electron will go into a molecular orbital. There's the 1s atomic orbitals, which are both.
So now if we look at here, this is the sequence. If you remember that in chapter 1, when we arrange the electron, okay, in the orbital, we start with 1s, 2s, 2p, and so on. 3s, 3p is according to the energy. So the same concept in molecular orbital, but instead of 1s, 2s, 2p, 3s, and so on, molecular orbital, remember, is the overlapping of the function, wave function of atomic orbital. So the molecular orbital is named as sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, and so on. So these are a fixed energy level of the molecular orbital. So you can see from here the energy is the lowest, getting higher and getting higher. So this has been calculated theoretically. So this is the energy level of the bonding domain and anti-bonding domain. So let's look at if we have oxygen. So you know oxygen have the total number of 8 electrons, and you have O2. So now you have 16 electrons to be arranged in the molecule, in the molecular orbital.
Both full, that go to make the 1s sigma and 1s sigma star, which are also both full. Then the 2s orbitals, also both full, which go to make the 2s sigma and 2s sigma star, again both full. Next we have the 2p orbitals. Each oxygen atom has 4 2p electrons. There are 6 2p orbitals total, 3 per atom. So we need 6 2p molecular orbitals. Those will be, in order of increasing energy, the sigma, pi, pi star, and sigma star. Remember, the starred ones are antibonding orbitals. As we take the 4 electrons from each oxygen atom and place them in the molecular orbitals, bottom to top, we end up with full sigma and pi orbitals, as well as half-full pi stars. Calculating bond order, we have 10 minus 6 over 2, which gives...
Okay, now this is quite easy for you to fill up. You have 4, so you fill up these 2 first and another 2. Now let's say you have 8, 2, 4, and 2, 4. So the first that you fill up is the lowest energy, definitely, sigma 2p, which is the bonding orbital, and then another bonding orbital, but pi 2p. So you fill up the degenerate, okay, one by one before you can pair the electron, okay? And now you are left with 2 electrons. There's 2 electrons. So this is how you fill up the 2 electrons. You have to fill up one by one. So no more electron. Now we can see that the electron only fill up singularly for each molecular orbital. Okay. Now, if you calculate the bond order, which is 10 electron is in the bonding orbital, and minus 6, which is in the anti-bonding, 2, 4, 6. Okay, so now we have the bond order equal to 2.
Us 2. That's why atoms in an oxygen molecule have a double bond between them. We can predict the covalent bonding behavior of any 2 atoms using orbital diagrams like this one. Let's look at nitrogen. Here, the bond order calculation turns out to be 3, which is why...
So before you can start calculating the bond order, try by yourself to fill up the electron in the molecular orbital. So nitrogen have 7. This is oxygen. Okay.
Atoms in a nitrogen molecule have a triple bond between them. Let's check comprehension.
Okay, let's stop here. So you can see, let's try for nitrogen. This is supposed to be nitrogen, not oxygen. So nitrogen have 7, 3, okay. So nitrogen and 2 means 7 plus 7, you have 14. So I'm sure that you can do this. 1s2, 1s2, and then you fill up. Another 2s, another 2s, you can fill up. So now you have about 8 to total of 8, 2, 4, 6, 8. So you have another 6 electron to arrange. Okay, so according to the principle, okay, first you have to fill up the bonding orbital, which is sigma 2p, and then you have to fill up the degenerate orbital pi 2p, single electron first and then pair it up, okay? And now looks like we don't have any more electrons, so this only up to here. So if you calculate the bonding order, the bond order is 10, 2, 4, 6, 8, 10, which is in the bonding orbital, minus 4. Okay. So now we have 3. So that should be the way of doing the electron configuration, the orbital diagram of, that's how we arrange electron in the orbital diagram for molecular orbital theory.